Open a spacesuit in vacuum and the human body does not explode. Blood does not instantly boil out of the veins. The body does not freeze solid, and consciousness does not vanish at the exact moment pressure disappears. Those images are useful for movies, but the real sequence is quieter, faster, and more dangerous. The first hard limit is not cold. It is oxygen. When external pressure collapses, there is no breathable air and no pressure to make normal breathing work. Oxygen already carried in the blood continues toward the brain for only a few seconds. NASA guidance estimates roughly 9 to 11 seconds of useful consciousness in near vacuum. In a documented chamber accident, a test subject remained conscious for about 14 seconds. The numbers differ because the starting oxygen level, decompression rate, and individual body all matter. Holding your breath would make the situation worse. Gas inside the lungs expands as pressure outside falls. If the airway is closed, that expanding gas can injure lung tissue. The safer emergency response during rapid decompression is to exhale rather than trap a full breath. This does not solve the oxygen problem, it only reduces one additional source of damage. The body does swell, but skin is much stronger than a thin balloon. It contains the tissues and prevents the dramatic explosion shown in fiction. NASA describes mild, reversible swelling during very short exposures. The circulation system also keeps blood under pressure, so blood deep inside intact vessels does not simply boil away. Surface moisture is different. Above roughly 63,000 feet, atmospheric pressure falls below the vapor pressure of water at normal body temperature. This boundary is called the Armstrong limit. Beyond it, water can change into vapor without being heated to 100 degrees Celsius. The process is called ebullism. Moisture on the tongue, eyes, and airways can begin to vaporize, while gas bubbles and swelling appear in exposed tissues. This is not the same as the entire body becoming a pot of boiling liquid. Internal pressure, skin, and blood vessels still matter. But ebullism can damage tissues, interfere with circulation, and combine with hypoxia. NASA technical literature treats it as a major spacesuit hazard alongside decompression sickness and lung injury. The best human evidence came from an accident, not an experiment designed to expose someone. During a 1960s pressure suit test at NASA's Manned Spacecraft Center, technician Jim LeBlanc's suit lost pressure inside a vacuum chamber. He later recalled feeling moisture on his tongue begin to boil before his vision faded. He lost consciousness, and the team immediately repressurized the chamber. Quick action prevented serious injury. That accident demonstrates two important facts. Brief vacuum exposure can be survivable if repressurization begins immediately, and the useful rescue window is measured in seconds. It does not prove that a person can safely remain in vacuum for a fixed time. Injury accumulates as the brain loses oxygen, tissues swell, and circulation becomes disrupted. After 1 or 2 minutes, survival becomes increasingly unlikely, but an exact universal death timer would be invented precision. Freezing is slower than most people expect. Space can be extremely cold, but vacuum contains almost no matter to carry heat away by conduction or convection. The body mainly loses heat by radiation and evaporation. That process is not instant. Direct sunlight creates the opposite problem. Intense solar energy and ultraviolet radiation can heat and burn exposed tissue. In space, hot and cold depend on radiation, orientation, and time, not simply the number printed as the temperature of empty space. A spacesuit prevents this entire cascade by doing far more than supplying oxygen. It maintains pressure around the body, removes carbon dioxide, controls temperature and moisture, shields the eyes, supports communication, and carries water and electrical power. Astronauts also pre-breathe oxygen before spacewalks to reduce nitrogen in the body and lower the risk of decompression sickness when moving to the suit's lower operating pressure. So the honest timeline begins with seconds of awareness, not an explosion. Hypoxia attacks the brain. Expanding gas threatens the lungs. Low pressure allows surface moisture and some tissue water to vaporize. Swelling and decompression injury follow. Temperature becomes a serious problem over longer exposure, but it is not the first killer. A spacesuit is not clothing. It is a pressurized spacecraft shaped around one human body.